Hello, my name is Gulko, and today I will be presenting my project titled Increasing Efficiency of Thermoelectric Generators in Low Temperature Differential Environments. Okay, so let's jump in. So the first thing we need to discuss is why I chose this project. So there are many sources of global energy: gas, coal, oil, solar, wind, nuclear, hydro, and all of these are great. We've been using them for a long time. But the problem is specifically gas, coal, and oil. They they create climate change, and if our temperature exceeds 2 degrees Celsius temperature rise, there will be a major disturbance in the Earth's environment, and this is really not good. We don't want this to happen. So to prevent this, we need to slowly switch to the other categories of solar, wind, and hydropower. So that's one of the reasons that I chose this project. So as we jump in, thermoelectric generators, or as I will call them through the rest of this presentation, TEGs, use a heat differential to produce electricity. When heat is applied to one side of the generator and cooling is applied to the other side, or some way for the heat to dissipate, the difference in heat causes electrons to flow through the module into the wires where the voltage can be measured, or we can use it to power things. So in the diagram on the bottom left, we see that heat can be dissipated and heat is applied, and through those wires, that's where we get the electricity. So the objective of my project. The objective was to test and increase the efficiency of thermoelectric generators so that we can use them in room temperatures, outdoor environments, so that we can try to reduce the coal, gas, and other stuff we can use and slowly shift towards the other sources of energy. My null hypothesis states that when we try to increase the efficiency or the voltage output of the system, it will not increase. And the alternate hypothesis is that if we do apply the parameters of heat sources, insulation, addition of other mechanisms, the efficiency or voltage output will increase. So now we move on to assumptions and questions that we can have. So the first thing we can assume is that the higher the heat differential is in the system, the higher the voltage produced by the system will be. So this is logical. But the main question here is, how much higher will it be? And if we increase the temperature range, but also the temperature at which the temperature range is, will we produce higher voltages? So for example, from 100 degrees Celsius to 150 degrees Celsius and 50 degrees to 100 degrees Celsius, will the 100 to 150, although it has the same 50 degrees Celsius range as the 50 to 100, will the 100 to 150 degrees Celsius system create more voltage or higher efficiency, even though they both have a 50 degrees Celsius heat differential? So another thing we might want to consider is outside factors that could raise the heat differential or increase the voltage or find a way to make it power an LED or some other items. So we can assume that there are several factors, but we want to try to find which ones are the most effective or useful. Here we'll be looking at specifically joule thieves and different heat sources that we can use that are naturally occurring. So as we go into the experiment, the materials, I listed them out here. Boiling hot water, cold water, we're going to use these as heat sources. We're going to use a person's hand as a heat source. We're also going to use ambient air or room temperature air. You're going to need a joule thief circuit. I used a thermoelectric generator Peltier module, like the one shown on the right. I used a multimeter to measure the voltage. Then to hold the hot water and the cold water, I got a container that was the same width as the sides of the module. This way I could apply it. I had aluminum foil for one of the tests we will see later that involves insulation, an aluminum bar also for the hot and cold water test, rubber gloves because we are handling wires here and there's a voltage, and we're going to use an LED because we're going to see if we can power it. So for the procedure, I have the control group, the joule thief circuit experiment, and basic instructions for all the experiments. I tested all these experiments twice, and if you actually read for the joule thief circuit experiment, we will be applying the joule thief to the cold and hot water system, TEG, that we will see in the next slide that will be described through the procedure. We want to measure the voltage while we still are applying the heat sources, so we still have the heat differential. And the reason that we tested twice is because on different days, we wanted to see if there were slightly different results, if the temperature varied, and so maybe that could have changed something, the ambient air temperature, the room temperature environment, it could have changed, humidity could have changed, so things like that we want to take into consideration. So we tested twice, and I took the average of those results. So here we see the cold and hot water test, and the hot water test. For the cold and hot water test, we applied a joule thief to it after we did the test by itself. We will see the results for that later. It gave us something interesting. For the procedure for the cold water test, it's pretty much the same for the hot water test, the hot water test, and the cold water test. They're very similar, except for that we're going to change the heat sources, and we're going to use aluminum bar. We're going to use a container to hold the water, and we're going to use an aluminum bar to see if maybe the heat will go through the aluminum bar without having to have direct contact with the thermoelectric generator hot side. So as we move on from our procedure, we go to the aluminum foil insulation test procedure. For this test, we will, rather than just using our hand, we will apply aluminum foil around our hand. We specifically want the shiny side of the foil to be facing inwards to touch the hand, and the dull side to be facing out, because the shiny side of the foil is the side that will trap heat in, and that's what we want. We want to see if we can insulate the heat to try to stop it from dissipating into the ambient air, because maybe that will help to increase the temperature differential, and we want to see if maybe there will be a higher voltage produced if we do this insulation. So as we go on to our results, we look at the data I have on these two charts on the right. We see all the experiments that have been conducted, and we see the voltage in millivolts that was received from the system, tested and received through the multimeter. And so the system with the highest voltage happened to be the joule thief system with the hot and cold water in the hot and cold water system, basically the same system. The joule thief, however, as we can note here, it did not increase the voltage, but it did power an LED. And because it did power an LED, that becomes very helpful. So as we look at the scatter plot, something very important to note here is between those second and third points and the fourth and fifth points, we can see that between the second and third points, there was about a 200 millivolt rise between 8.91 degrees Celsius, and between the same temperature differential of 8.91 degrees Celsius, it later rises around 300. So like I said earlier, we wanted to see if the 50 degrees Celsius to 100 degrees Celsius range would produce less energy than, or less voltage than the 100 degrees Celsius to 150 degrees Celsius range. And so as we can see, as we go to a higher temperature, it increased from 200 voltage in millivolts to 300 millivolts increase. And here we can see this simply just shows that because we tested these on 2 different days, we can see the second test and the first test, second test in red, first test in blue. The first test is significantly performing lower, and this could be possibly due to temperature differences in ambient air and other things like that because of humidity. So we see that they are not very reliable. So as we go to our conclusion, we can see that thermoelectric generators generally thrive in environments where they have a large temperature differential. They aren't very useful in this kind of environment, as we have seen, because there isn't a very high temperature differential. Null hypothesis was rejected because the efficiency did decrease. The insulation test showed that the voltage could be increased, but maybe it was just due to different days, different temperatures. So with future study, I could possibly use transistors, transformers, and try to use other kind of gadgets. Thermoelectric coolers might be looked at too. And that concludes my project.